by 2 plus 50, that is 150 mm. A3 area of top flange, that is 200 multiplied by 50, 10,000 mm square, and Y3 is the distance of the CG of the A3 from the bottom face, that is 50, that is the thickness of bottom flange, plus 200 available width, that is available total thickness of wave, plus 50 by 2 thickness of flange divided by 2, that is 275 mm. So once we know all these things, we have to put up this value in this equation, and if we put up this over here, if we refer, then it is 6500 multiplied by 25 plus 10,000 multiplied by 150 plus 10,000 multiplied by 275 divided by the summation of area, and we found out the value of YB. Remember, this is my YB, that is 166.51 mm. I found out the depth of neutral axis from the bottom fiber is 166.51 mm. So if you want to refer that particular figure, please refer the figure. This is the section which is given to us. This line, dotted line, is our neutral axis, and from that neutral axis this bottom fiber is of 166.51 mm. Total depth minus 166.51 mm, we achieve the distance of neutral axis to the top fiber, that is 133.49 mm. So this thing, first step we achieve right now. Now we have to use this value to find out the value of I. See over here. Now I is equal to I1 plus I2 plus I3. What is I1? Moment of inertia of bottom flange about neutral axis. When I want to find out the moment of inertia of the bottom flange about the neutral axis, I have to use the concept of parallel axis theorem, that is moment of inertia of bottom flange about an axis passing through its CG plus A1 into distance of its CG from neutral axis square, AH square. So 1 by 12 BD cube 130 into 50 cube plus 6500 into bracket the distance 166.51 minus 25 square, and we achieve this value as the value of I1. Similarly, we can find out the value of IT over here, that is the moment of inertia of the wave about neutral axis, that is equal to moment of inertia of wave about an axis passing through its CG plus A2 into h square, distance of CG from neutral axis square. Simplify once again, 1 by 12 BD cube, B is 50, D cube is 200 cube plus area multiply by interesting point YB, that is distance from neutral axis to bottom fiber, minus the distance of CG from the bottom fiber, that is 150 square, and we achieve this value. Next, I3 is the moment of inertia of the top of flange about neutral axis, that is moment of inertia of the top flange about an axis passing through its CG plus A3 into distance of its CG from neutral axis square, and we achieve 1 by 12 BD cube 200 into 50 cube plus 10,000 multiply by. Now I have to find out Y3, that is the distance of CG from the neutral axis, that is 275 minus 166.51 square, we achieve this value. By doing the summation, I is equal to I1 plus I2 plus I3, we achieve this much value of total I for given I section. If you do not understood how to find out Y2 and Y3, let us we use a tabletop within 2 minutes. Let us go here. So refer a figure. This is a given I section. Fine. This will be my neutral axis, and from the formula we found that it is 166.51. Now this is our first CG of the first part. This is my first part. This distance is of 50 by 2. So what will be this? This is my y1. Please understood carefully. Now if this is the CG for the second part, that is of wave, then this will be my y2, and this is the CG from the top flange. This will be my y3. So what we did to find out the y3, this distance is available to me previously 275 minus this. So y3 will be available 275 minus 166.51. I think you have understood very well this one. And this y2 will be found out by 166.51 minus this distance. This available distance to you, that is of 150. So this y2 is equal to 166.51 minus 150. Very simple. So now let us go ahead. Now the distance of CG from the upper top of fiber is nothing but the total depth minus distance from the neutral axis to the bottom fiber, that is YB or Y bar, that is 300 minus 166.51, that is 133.49 mm. Now the distance of CG from the top fiber is 166.51 mm. Would like to ask the question, which one y we have to use to find out the value of z? Obviously z is equal to I by y max. I have to use y max, that is 166.51 mm, to find out maximum bending stress. So maximum bending stress we have to using the first equation, m over I is equal to f max by y max. So f max is equal to m over I into y max. Given m value is 40 into 10 raised to 6, divide by the value of I that we have found out, multiply by 166.51, we found out the value is of 23.38 megapascal. So the maximum bending stress is nothing but 23.38 megapascal Newton per mm square. And the stress distribution diagram is shown in this particular figure. Please clearly precise, as we have used this 166.51, the value of the maximum stress is over here. Now the question may arise, what will be the nature of this? Very good questions that has been asked over here. Let us refer the same thing on this tabletop. Now please refer the tabletop. The given beam, it is of bracket, that is of cantilever, with any kind of load, and the moment generated is equal to 40 mega Newton into meter, that is 40 mm into 10 raised to 6 Newton mm. The diagram of bending moment is like this. This is the value m which is given to us, negative. What will be the nature of bending moment? What will be the nature of bending moment? The nature of bending moment for a cantilever beam is of, if I will take a section over here clockwise, this nature is known as hogging bending moment. And what do you mean by the hogging bending moment? Hogging bending moment creates tension on the top, compression in the bottom. So at a section, if this is my section I, at this bottom section compressive stresses will be developed on the top tensile stresses will be developed. So the given answer of this my bending stress is of the nature of compressive bending stress. This is our answer. I wish you have understood this problem very well, and we are going ahead with the next problem. Please refer this problem. A cast iron I section as shown in the figure. So the I section, please see the figure very precisely. See the top flange, bottom flange. It is very much clear that the given section is of unsymmetrical shape. Now the beam is simply supported on a span of 5 meter. Interesting point, the beam which is given is of the simply supported and the span which is of 5 meter. Now if the tensile stress is not exceeds to 20 megapascal, it has been stated that the limitation on the bending stress, specifically the tensile stress, is limited to 20 megapascal, 20 Newton per mm square. What is the question then? Determine the safe uniformly load which the beam can carry. Question is about what will be the load acting on the beam which is safely carried by the beam. Also find the maximum compressive stress. A very good question which has been asked to you. Let us refer what will be the given data in this particular problem. First, a section is given to us. So for a question of bending stress, when a section is given to us, our intention is to find out the I value, to find out Z. Now to find out the value of I, moment of inertia, I have to first of all find out the center of gravity, that is the centroid of the section. So this is the first step. Now the length of the beam which is given to us as 5 meter and the type of the beam which has been stated as simply supported beam. Maximum tensile stress, that is of 20 megapascal, 20 Newton per mm square. It is important to find first the CG, means centroid of the section, and then the moment of inertia. So what we have to do right now? To find out the CG, I have to divide my figure into the 3 parts, like first part, second part, and the third part. I have to divide my figure into these 3 parts. Let us do right now over here. So y bar is the distance of the CG from the bottom face. So y bar is equal to a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. Now a1 is the area of bottom flange. Refer the previous figure. What will be the area of bottom flange? It is this width of flange multiplied by the depth of flange is the area of flange, that is 160 multiplied by 40. We achieve 6400 mm square, where the y1 is the distance of the CG of this area A1 from the bottom face, that is nothing but 40 by 2, that is of 20 mm. I think you have understood very clearly, as these things we have discussed in the previous problem. Now A2. A2 is the area of web. What will be the area of web? Please refer the previous figure. Area of web is nothing but the thickness of web and available depth, that is the 200 multiplied by 20 is the thickness of web, and we found out 200 multiplied by 20 is nothing but the 4000 millimeter square, where the y2 is the distance of the CG of the area A2 from the bottom face, and that is nothing but 40, that is the thickness of flange, plus 200 by 2, that is the 40 plus 100, that is 140 mm. Next, A3. A3 is the area of the top of flange. The top flange which has been given to us is of 80 mm flange width, 20 mm thickness, 80 into 20, that is the area available to us, and that is 1600 mm square, while the Y3 is the distance of the CG of area A3 from the bottom face, that is nothing but 50 plus 200 plus 20 by 2, that is of 260 mm. Once we found out A1, A2, A3 and Y1, Y2, Y3, we have to replace this value in this equation. So if we see, we got, this is the equation, 6400 multiplied by 20 plus 4000 multiplied by 140 plus 1600 multiplied by 250 divided by the total area of the three different rectangles from which the I section which has been made up, that is 6400 plus 4000 plus 1600, and we found out 90.66 mm. We found out Y bar is 90.66 mm. Hence, the neutral axis is at a distance of 90.66 mm from the bottom face. So, 260 minus 90.60, 169.34 from the top face. If you want to refer the figure is over here. The total available depth is 200 plus 20 plus 40. It is 50, think. So total available depth is this one, and the available total depth is the 260. How it is 260? 220 plus 40, 260. Minus this YB, that is 90.66. So available depth is, total depth, that is available depth from neutral axis to the top fiber, is 169.34 mm. Next step is to find out the value of I, that is the moment of inertia about the section about neutral axis. So I is equal to the summation I1 plus I2 plus I3. So what is the I1? I1 is